thus far, we've talked about the three states of matter, okay, according to kinetic molecular theory, that is solids, liquids, and gases. And we've discussed both the macroscopic as well as microscopic differences between them. So we're now going to talk about how matter actually changes from one state to another. We refer to such changes as changes of state, or sometimes known as phase changes. Changes of phase are always accompanied by energy changes. Matter must gain or lose energy in order to change phase. So let's consider the following schematic diagram. In order for a solid to become or change into a liquid, energy must be added, okay, in some form to basically move the particles further apart. Okay, the same can be said for turning a liquid into a gas. You've got to add energy, okay, to move those liquid particles further apart, okay, to become the gas. Remember that one of the ways that we talk about the differences between these states of matter is simply the particle spacing, okay, how much space there is between the particles. So as the diagram illustrates here, you can see that it takes a lot more energy to convert matter from the liquid state to the gaseous state, okay, than it does to convert matter from the solid state to the liquid state. This is because we have to move the particles much further apart in going from a liquid to a gas than we do in going from a solid to a liquid. That means that more energy is required. Okay, when a gas turns into a liquid, okay, well, energy has to be released from the matter. Okay, and similarly, when a liquid turns back into a solid, energy has to be removed from the liquid, okay, and released into the environment. So it's important to realize that energy can come in the form of, okay, either kinetic energy or potential energy. So when particles of matter experience a change in kinetic energy on the microscopic level, this corresponds to a change in temperature on the macroscopic level. Okay, as we've seen previously, when the kinetic energy of the particles increases and the particles move faster on average, okay, the temperature of the matter increases. Okay, so really we say that temperature is a measure on average of the kinetic energy of the particles in that sample of matter. When particles move closer together or move further apart from each other, okay, without changing the speed or kinetic energy, this represents a change in potential energy, okay, on a microscopic level. This is what we call a phase change. Okay, since the particles are attracted to each other, it takes energy to move them further apart. And when energy is added to do this, we are increasing the stored energy in the particles. That is increasing the potential energy of the particles. Conversely, when particles move closer together, okay, that stored energy gets released to the environment. And this is, again, what we call a phase change. So we can think of when we add energy, okay, from to a solid and turn it into a liquid, okay, that energy gets stored as potential energy in the particles to move them further apart. The same can be said for converting a liquid into a gas. Okay, we've got to add energy that gets stored as potential energy in the particles to move them further apart. Okay, so you see here that when you add energy, that energy can go into either increasing the speed or kinetic energy of the particles. That corresponds to a temperature change, or it can go into changing the particle spacing, that is moving the particles further apart or closer together, and that change in particle spacing is what we refer to as a phase change, okay, where we're changing the potential energy stored in the particles. We're now going to spend a few minutes classifying and explaining various changes of phase that matter can experience. Some of these terms will be familiar to you, some of them probably will not. Now remember that a change of phase or change of state involves matter transitioning or changing from a starting state to an ending state. We'll start by discussing a change of phase known as evaporation. Evaporation is the process whereby particles on the surface of the liquid gain enough kinetic energy to escape the surface and become a gas. This only applies to particles on the surface. When particles deep beneath the surface can change from a liquid to a gas, okay, then we call that process boiling. But both of these changes of phase, whether we're talking about evaporation or boiling, involve the transition from a liquid state to a gaseous state. Now, in order for the particles on the liquid surface to escape their attraction for the liquid particles beneath them, they must gain energy. Where does this energy come from? Well, it comes from the kinetic energy of the other particles beneath them. Okay, this microscopic form of kinetic energy gain is what we call thermal energy or heat. Right? Remember we said a long time ago that thermal energy is simply a microscopic form of kinetic energy. So those particles on the liquid surface, okay, through the collision process, they gain kinetic energy from the particles below them, okay, when collisions happen. And if they gain enough kinetic energy to escape the forces of attraction holding them into the surface, okay, that is the forces from the particles beneath them, then they can turn from a liquid into a gas. So we can think of evaporation as a cooling process, since only the liquid particles with the greatest energy can escape the liquid surface. So when those particles with the greatest energy escape, this leaves behind particles of lower average kinetic energy. So a really great example to understand this is to ask the question, why do we sweat? Okay, or why do we perspire? Well, when we perspire, water molecules on the surface of our skin gain energy from our body and escape our skin in gaseous form. Okay, now because the energy required to change the liquid water on the surface of our skin into a gas, okay, comes from the body itself, right? Okay, so those liquid water molecules on the surface of our skin must gain energy from our body, enough kinetic energy, okay, to be able to turn those liquid particles into gaseous particles. And when this happens, okay, the higher energy gas molecules leave the body, okay, and when they do so, that leaves the overall body temperature, okay, to be a little bit less. The overall body temperature decreases when the fastest moving particles on the skin escapes. Okay, that's why it cools down our body. The phase change that we call boiling is certainly a phase change that you're all somewhat familiar with. Boiling is the process where a liquid turns into a gas at the boiling point temperature. So, like evaporation, boiling involves a change in phase, okay, from a liquid to a gas, and like evaporation, energy must be added to the liquid molecules to turn them into gaseous molecules. Also, like evaporation, we can think of boiling as a cooling process, since liquid particles must gain enough energy to become a gas. Okay, and when they do so, this leaves behind particles of lower energy on average. Okay, so how is boiling different from evaporation? Well, remember we said that, okay, in evaporation, it's only the particles on the surface, okay, that can gain enough energy to escape the liquid phase and turn into a gas. But when we talk about boiling, okay, we're talking about the liquid particles, being at a temperature high enough, what we call the boiling point temperature, such that all particles in the liquid, not just those on the surface, but all particles in the liquid, okay, have enough energy to become a gas. So this requires a much higher temperature, okay, than does simple evaporation. You know that if you put a cup of water out in your room at room temperature, okay, that evaporation will take place well below the boiling point temperature. Okay, but for boiling, we're talking about not just the particles on the surface having enough kinetic energy to actually turn from a liquid to a gas. We're talking about all the particles having sufficient energy to make that transition from the liquid state to a gaseous state. That requires a much higher temperature. Okay, so when water is boiled in a pot and bubbles form, what exactly is inside a bubble, okay, in that boiling pot of water? Okay, now a lot of people here, okay, I'm sure you're not included in this group, but a lot of people say, oh yeah, that's air inside of the bubble. Okay, but think about it. Okay, what is boiling? It's the change of phase from a liquid to a gas. So the bubble forms when liquid water turns into gaseous water or steam. So what's inside the bubble is gas. It's gaseous water, not air. Okay, it's steam. That's what's inside a bubble when water boils. Gaseous water. The next phase change we'll talk about is one we call condensation. Condensation is the process where gaseous particles collide with the liquid surface and become part of the liquid again. When they do so, they release energy to the liquid in the process. So when we think about it, condensation is really the opposite of evaporation. Remember we said that in evaporation, those particles on the liquid surface can gain enough energy to escape the surface and become a gas. Now we're talking about those gaseous particles near the surface that when they collide with the surface, okay, they become a liquid again. Okay, they get trapped by the surface and the gas particles, okay, lose their freedom and they now become part of the liquid state. When this happens, energy is removed from the gas. Okay, in order for the gas to become a liquid, it must lose energy. Okay, and this is why we say that condensation is a warming process. When those fast-moving gas particles collide with the liquid surface and okay, make the transition from a gaseous state to a liquid state, they lose energy. Okay, and that energy lost stays in the liquid and it increases the overall energy of that liquid, thus warming it. So in looking at an example here, we're asked the question, why are human climates so uncomfortable when compared to dry climates? Okay, well, when we think about it, okay, when we talk about a human climate, okay, which can be very, very uncomfortable in the summertime, okay, or even in the wintertime for that matter. Well, in a human climate, the gaseous water molecules in the air, okay, can now condense on your skin. And as we just said, when they do that, they release energy to your skin and to your body, okay, warming your body up. That's uncomfortable, okay. In a dry climate, okay, on the other hand, we have much more evaporation taking place than we do condensation. And when that rate of evaporation is greater than the rate of condensation, okay, we can say that overall energy gets removed from your body. Okay, but in a humid climate, the opposite is true. Okay, the rate of condensation far exceeds the rate of evaporation, in which case, okay, overall energy is being added to your body, warming it up, making you feel uncomfortable. So we're now going to take a look at what I would consider a pretty cool demonstration, okay, to see how both evaporation and condensation make this dunking bird operate. So this toy dunking bird operates by the evaporation of the ether inside the body and by the evaporation of water from the outer surface of the head. So when you look at the apparatus, you can see that the lower body contains liquid ether, which evaporates very rapidly at room temperature. Ether is what we call a volatile liquid, meaning it turns very readily from a liquid into a gas. Okay, it doesn't take a lot of energy for that to happen. And as this liquid ether evaporates, turning from a liquid into a gas, it creates pressure. And that pressure pushes the ether up the tube, okay, from the bottom of the bird up to the head. So when that ether in the upper part of the tube near the head of the bird, okay, it will then condense back into a liquid because the head is cooled by the evaporation of the water from the outer felt covering. So when the weight of the liquid ether in the head is sufficient, the bird will pivot forward, take a drink, okay, and this permits the ether to run back to the body. Each pivot wets the felt surface of the beak and head, okay, and the cycle is then repeated. The process we call sublimation is a phase change you're probably less familiar with. What is it? Well, sublimation is the process where particles on the surface of a solid can gain enough energy to become a gas directly without passing through the liquid state. So when we compare the process of sublimation to that of evaporation, all we have to do is replace the word liquid surface with solid surface, right? Evaporation is a process where particles on the liquid surface can gain enough energy to become a gas. Here we're saying that sublimation is a process where, okay, particles on a solid surface particles can gain enough energy to become a gas directly, okay, without passing through the liquid state. So here we're talking about a solid turning directly into a gas. And of course, you would expect that energy must be added to those solid particles in order for this to happen. We can once again say that sublimation would be a cooling process, since particles on the solid surface must absorb energy from, okay, the other particles, the remaining particles that don't sublime. Okay, and when they do so, the particles that are left that don't turn into the gas now have lower energy on average. Okay, so the solid that remains with those particles having lower energy, it will be at a lower temperature. That is why we say it is a cooling process. Okay, nice example of this, which, okay, if you're observant, I think you would have experienced this. Have you ever noticed that if you look at ice cubes in your freezer, okay, ones that don't get regularly used, they will get smaller in time. Okay, well, why is that? Well, okay, it's because of sublimation. You can guess that, okay, those solid ice particles, the solid water molecules on the surface of the ice cubes, some of them will be able to gain enough energy to actually enter the gaseous state. That's sublimation. When they do so, when those solid particles leave the solid surface and become a gas, okay, that leaves less overall molecules on your ice cube, making it become smaller in time. This phase change that we call melting, okay, is the process whereby a solid turns into a liquid at the melting point temperature. As anyone who has ever eaten an ice cream cone on a hot summer day well knows, okay, energy must be added to the solid in order for it to become a liquid. So we can say here that when melting occurs at the melting point temperature, all of the particles have enough energy to enter the liquid state, not just those particles on the surface. In considering an example here, we'll consider the case of the melting of metals. Now, we're very familiar with the melting of water because that happens at a temperature, okay, of 0 degrees Celsius, a temperature which, we can experience in our freezer, okay, whereas the melting of metals happens at very, very high temperatures on the order of several hundreds of degrees Celsius. So in our normal everyday experiences, we see most metals as being solids, okay, not liquids. But in order for metallic objects, okay, to take their everyday form, like let's say the door of a car or a paperclip, the metal must be melted, okay, must be converted from a solid into a liquid, then poured into some sort of mold, okay, in order for its desired shape to occur. And lastly, the process that we call freezing, okay, is the process whereby a liquid turns into a solid at the freezing point temperature. Freezing is really the opposite of melting. Okay, remember we just said that melting is the process whereby a solid turns into a liquid at the melting point temperature. Okay, now we're saying that freezing is the process whereby a liquid turns into a solid at the freezing point temperature. How do the melting point temperature and freezing point temperature compare? They're one and the same. In other words, the temperature with which a substance melts, goes from the solid state to the liquid state, is exactly the same temperature at which a substance freezes. Okay, that is, turns from the liquid into a solid. So for example, water, okay, has a freezing point and a melting point of 0 degrees Celsius. So we can say that when, okay, some substance freezes, okay, for example, let's say liquid water becomes solid water, then energy must be removed from those liquid molecules, okay, in order for that to happen. And this will nicely explain the answer to the example we're going to consider here. That is the process of making ice cubes. Have you ever noticed the warm air that comes out of the back of your refrigerator or freezer? Okay, well, what's behind that? Well, if we say that energy must be removed from liquid water in order to freeze it, okay, in order to convert the liquid water into solid water or ice, where does that energy go? Okay, well, it must be removed from your freezer compartment, and it ultimately ends up as that hot air that is blowing out of the back of the freezer, okay, and then enters your kitchen in the form of heat. So we're now going to take a look at an example of what we call a heating curve to better understand the above processes that we've just finished describing, as well as the energy changes associated with them. Okay, a heating curve or a cooling curve is simply a graph of temperature versus time for a substance that is either being heated or cooled at a constant rate. Okay, for example, in the example we're looking at here, we're considering 1 kilogram of ice, which is being heated in a pot on a stove at a constant rate. And this graph of temperature versus time, okay, data is collected, and then we, okay, graph that data. And when we do so, the graph takes on this characteristic shape that you see in the right-hand portion of your screen. Now, this basic shape would occur for any substance that we were heating, not just for water. So we want to try to explain the shape of the graph. Okay, what is the meaning of these flat portions of the graph that follow each of the slope portions of the graph? So let's take a closer look at each segment of the graph. And one more thing to try to clarify this. Notice that our heating curve or cooling curve, a graph of temperature versus time. On the horizontal axis, okay, we're graphing time. Remember that we are adding heat at a constant rate. So we're assuming that in a given amount of time, we've added a given amount of heat. So for example, if in 5 minutes we've added a certain amount of heat to our sample, okay, we can assume that in 10 minutes we've added twice as much heat to the sample. That's what we mean by adding heat at a constant rate. So let's start by considering the first slope portion of our graph, what I'm calling AB here. And if we try to explain this, we're going to look at an explanation from a microscopic point of view, trying to explain the energy changes taking place, as well as describing this from a macroscopic point of view. What is happening? Okay, well, you can see on your graph here that in going from A to B, the temperature of our sample is increasing. And from our understanding of the meaning of temperature, temperature being a measure of the average kinetic energy of the particles that make up the substance, here, the heat that we're adding is going into increasing the kinetic energy of the particles. Okay, and that's what's happening microscopically here. The heat that is increasing the kinetic energy, we can describe this macroscopically by saying that's why the temperature is increasing here. So since we're starting out with solid water, that is water in the solid phase, what we call ice, we are adding energy to the ice, and the temperature of that ice is increasing. When we come over and take a look at, okay, the second portion of our graph, this flat portion here we call BC, okay, what is going on there? Okay, well, you want to notice that we are adding energy at a constant rate, we're adding heat at a constant rate, yet when you look at going from B to C, you'll notice that the temperature does not change. So what is happening to that heat that we're adding? Okay, well, if the heat is not going into increasing the kinetic energy of the particles, remember that's what temperature is. Where's it going? It's going into increasing the potential energy of the particles, right? So we're talking about water molecules in a solid state. They have a certain amount of kinetic energy. We're adding energy. We're not increasing their kinetic energy, but we're increasing their potential energy. What are we doing? We're making them move further apart. Not increasing their vibrational speed, we're moving them further apart. Remember we said that is what a phase change is. That is the only difference between a solid and a liquid. Okay, we can say that, you know, in a solid the particles are close together, in a liquid they're further apart. So we're bringing about the phase change by not increasing the kinetic energy of the particles, but by increasing their potential energy to move them further apart. Energy must be added for that to happen. So this is where the phase change happens. This is where the solid water, ice, is now melting to becoming liquid water at the melting point temperature. For water at normal atmospheric pressure, this happens at 0 degrees Celsius. So over here in this portion B to C, we can assume that for water, this is at a temperature of 0 degrees Celsius. We're adding heat to the ice cubes. We're not actually increasing the temperature of the ice. Okay, we are just bringing about the phase change, turning the solid into a liquid. Okay, the next portion of the graph CD here, you'll notice that once again, the energy we add there goes into changing the temperature. Okay, so here we can say that in that portion of the graph, we're adding heat. Where's it going? It's now increasing the kinetic energy of the particles, okay, to bring about a temperature change for the liquid water. We're bringing the liquid from 0 degrees Celsius all the way up to 100 degrees Celsius in the liquid phase. Okay, once we get now over here to this second flat portion of the graph, once again, we are not changing the temperature. We're adding energy, we're adding heat, but we're not changing the temperature. Okay, what's happening to that heat that we're adding? Okay, well, it is going into increasing the potential energy of the particles once again to bring about the phase change. This is where the liquid water molecules, okay, which are now moving much faster than the solid ones, okay, for that portion of the graph DE, we're not making them move faster, we're simply moving them further apart so that they can turn from a liquid into a gas. That is the phase change that we call boiling. We're adding energy, we're increasing the potential energy of these particles to move them further apart so that the liquid molecules enter the gaseous state. And finally, now that all the liquid molecules have turned into a gas, that last portion of the graph EF, once again you see that the heat we add goes into increasing the kinetic energy of the particles, which is now, okay, from a macroscopic perspective, goes into increasing the temperature of those gaseous water molecules as steam, okay, to increase the temperature. So here we see the characteristic shape of a heating curve, okay, where the flat portions represent phase changes. The energy added goes into potential energy, whereas the slope portions of the graph represent temperature changes, where the heat being added goes into increasing the average kinetic energy of the particles in the substance. We alluded to the concept of latent heats in the previous slide, but didn't really define them in any concrete way. So let's do it here in this slide. As we said in the previous slide, energy must be added to a solid at the melting point temperature in order to convert it into a liquid. This added energy increases the potential energy of the particles as they move further apart. Likewise, energy must be added to a liquid at the boiling point temperature if we wish to convert it into a gas. Again, this energy takes the form of the potential energy of the particles as those particles move further apart. The latent heat is really nothing more than the amount of heat, the amount of energy that must be added or removed from a substance in order to bring about the phase change. Specifically, when we talk about the latent heat of fusion, we're talking about the amount of energy needed to change 1 gram of a substance from a solid into a liquid at the melting point temperature. It turns out for the case of water, for example, that it takes 334 joules of heat to convert 1 gram of water from solid ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So you see here, when we talk about the latent heat, we're talking about the energy added just to bring about the phase change, not to increase the temperature of the substance. When the reverse process occurs, okay, that is when liquid water turns back into solid ice, we can similarly say that 334 joules of heat is removed from each gram of water in order to bring about that phase change. So in a similar way, we can talk about the latent heat of vaporization as being the amount of heat or energy needed to change 1 gram of the substance from a liquid into a gas at the boiling point temperature. So it turns out for the case of water, it takes 2,260 joules of heat to convert 1 gram of liquid water at 100 degrees Celsius into gaseous water or steam at 100 degrees Celsius. Okay, and when we look at the reverse process, okay, when that occurs, in other words, when we convert steam, gaseous water, that is steam, back into liquid water at 100 degrees Celsius, we can say that 2,260 joules of heat is removed. So you'll notice here, when we compare these latent heats here, okay, that we said 334 joules of heat is required per gram of water to go from a solid to a liquid, but that 2,260 joules of heat is required per gram of water to convert it from a liquid to a gas. Okay, and this should make sense because, as we said previously, the amount of energy required to go from a liquid to a gas is much more than to go from a solid to a liquid. Why? Because we're moving those particles much further apart to go from a liquid to a gas. Okay, we're increasing the potential energy of those particles by a whole lot more which, of course, requires more energy.
So let's review and generalize some of these concepts we introduced in the previous slides. Specifically, we're taking a look at the energy changes involved in the calorimetric process. We'll look at these energy changes from both a macroscopic and microscopic perspective. So when we add heat to an object and there's no phase change involved, the heat added simply goes into increasing the temperature of the object. Similarly, when heat leaves an object and there's no phase change involved, the object's temperature drops. When there is a phase change taking place, what happens to that heat that we add? The heat added or the heat removed is required to bring about the necessary phase change. From a microscopic perspective, when heat is added to an object and no phase change takes place, the heat simply increases the kinetic energy of the particles in the object. Remember, that's what temperature measures. It's a measure of the average kinetic energy of the particles that make up an object. Likewise, removing heat from an object when no phase change occurs causes the particles to lose kinetic energy, thus lowering the temperature. So what happens during a phase change? How come heat is added yet the temperature doesn't increase? This is because the heat that gets added goes into increasing the potential energy of the particles. Generally, usually moving them further apart. So remember those flat portions of the heating curve graph. What that suggests is that we're adding energy to our object, yet there is no change in temperature, which means there is no increase in the kinetic energy of the particles. But conservation of energy tells us that if not kinetic energy, it's the potential energy of the particles that is increasing in this case. Okay, we have to basically move those particles further apart. Sometimes we think of that as the process of bond breaking. Likewise, when heat is removed from an object, the temperature doesn't drop during a phase change, and we can say the opposite. Okay, we can say that the particles are losing potential energy in the process of them moving closer together. We think of this as a bond forming process. When it comes to calculating energy changes, when it comes to solving calorimetry problems, when no phase change is involved, and we're simply talking about a temperature change, we use the equation we know and love, Q equals mc delta T. When there is a phase change involved, however, okay, then we're talking about a heat of fusion or a heat of vaporization, in which case we can calculate the amount of heat added by multiplying the mass by the latent heat. Okay, either the latent heat of fusion or the latent heat of vaporization.
And lastly, in this slide, let's take a look at applying the concept of latent heats to a couple of examples. So in our first example here, we're asked, why does a 100 degrees Celsius steam burn hurt more than a burn from boiling water at the same temperature? So let's start by considering the case of water which is boiling, which is at 100 degrees Celsius. The fact that those water molecules in a liquid state are at a high temperature, at 100 degrees Celsius, means that they possess a lot of kinetic energy. That's what temperature measures, right? It's a measure of the average kinetic energy of the particles. So if those liquid water molecules come in contact with your skin, they can certainly transfer some of that large amount of kinetic energy to your skin, thus causing a burn. But let's now consider the case of gaseous water molecules at the same temperature. In other words, what's the difference between liquid water at 100 degrees Celsius and gaseous water or steam at 100 degrees Celsius? Well, we said that The difference between the liquid and the gas is that for the gas, those particles are further apart. How do they get further apart? Okay, we had to add energy in the form of heat to increase their potential energy to move them further apart. So those steam molecules, even though they're still at 100 degrees Celsius, just like the water molecules, they possess more energy. How much more energy? An amount of energy equal to the latent heat of vaporization, which we said for water was about 2,260 joules of energy per gram of water. So when those steam molecules come in contact with your skin, okay, they are going to, at a much lower temperature, they're going to condense, meaning they are going to turn from a gas back into a liquid. And when they do so, they will transfer that latent heat of vaporization, okay, to your skin, causing a much more severe burn than just the liquid water molecules would cause. All right, so let's take a look at one more example here. And this may be something that you've come across before. If there's going to be a frost outside, which very often happens here in Modesto, you're very often advised to water your plants, okay, in the early evening before the air temperature drops to the freezing point. Okay, why is it? Why is it that water helps protect them? Well, having a layer of water on the outside of the plants, okay, let's think about what's going on as the air temperature continues to drop and get closer to the freezing point. When that air temperature finally reaches the freezing point, okay, while the liquid water on the outside of the plants, that must lose the potential energy, okay, that we would call the latent heat of fusion, in order for the liquid water at the freezing point to turn into solid water at the freezing point. Okay, remember we said that, okay, you know, it's about 330 joules per gram of energy that will be lost by liquid water, okay, when it freezes and becomes solid water. Where does that energy go? Well, if this is a layer of water on the outside of the plant or fruit in question, that energy which is lost goes into the plant itself. Okay, and by adding that little bit of energy to the plant, equivalent to the latent heat of fusion, this can keep the plant a little bit warmer, okay, and prevent it from reaching the freezing point a little bit longer. Okay, hopefully, you know, preventing the cells in it from bursting, which is what happens when the plant actually freezes. So let's now take a look at what we've been talking about in the previous slides involving heating curves and latent heats of fusion and latent heats of vaporization. Let's apply this to a quantitative problem. Okay, and in this problem here, we're asked how much energy is required to change a 1 kilogram block of ice at negative 20 degrees Celsius to steam at 120 degrees Celsius. So the first step in any one of these problems is always to identify the temperatures where the phase changes occur in the problem. So if we're going from an initial temperature of minus 20 degrees Celsius to a final temperature of 120 degrees Celsius, in this case the substance we're talking about is water, then we are going to experience two phase changes. For water, you probably don't have to look up the melting and boiling points. You notice that the first phase change, where water turns from a solid into a liquid, happens at 0 degrees Celsius. The second phase change, where the liquid water turns into a gas, happens at 100 degrees Celsius. But if this were a substance you were less familiar with, you look up that substance in a table, you find out, okay, what the melting point temperature is and what the boiling point temperature is, and that will inform you what phase changes will take place in your problem. So in this problem here, okay, we've got two phase changes, and we're going to start the problem by saying, well, we're starting with ice in a solid form at negative 20 degrees Celsius. We will add a certain amount of heat to bring that solid ice at negative 20 degrees Celsius up to solid ice at 0 degrees Celsius. This does not involve a phase change. It involves a temperature change only, in which case we can use Q equals mc delta T to figure out how much heat must be added. So we plug in the numbers here. We're talking about a mass of 1 kilogram. We look up, and by the way, I want to point out here that the specific heat capacity of ice is different from liquid water, which is different from gaseous steam. Okay, so you would look these up in a table. For ice, okay, from the table, it's about 2090 joules per kilogram degrees Celsius. Here we are going from, okay, 0 to negative 20 degrees Celsius, our starting temperature, up to the melting point where the phase change occurs, which is 0 degrees Celsius. So our delta T is 20 degrees Celsius. When we do the number crunching, it turns out that it will take about 41.8 kilojoules of heat to accomplish that, to bring solid ice at negative 20 up to solid ice at 0. The next step now is to bring about the phase change. How much heat must be added, okay, in the form of the latent heat of fusion in order to turn 1 kilogram of ice at 0 degrees Celsius to 1 kilogram of liquid water at 0 degrees Celsius. So here, there's no temperature change. The heat added is simply the mass of the substance times the latent heat of fusion, which once again you look up in a table for water. Mass of 1 kilogram, from the table we get about 3.33 times 10 to the 5th joules per kilogram. We do the number crunchy, that's about 333 kilojoules of heat to convert 1 kilogram of solid ice into liquid water at the melting point temperature at 0 degrees Celsius. The next step, once we've converted everything into liquid water, we now must raise the temperature of that liquid water from 0 degrees Celsius to 100 degrees Celsius. This is strictly a temperature change. There's no phase change. We use Q equals mc delta T. Again, the mass of 1 kilogram. The specific heat capacity for liquid water is about 4,180 joules per kilogram degrees Celsius. We're talking about a temperature change here of 100 degrees Celsius. Okay, when we do the number crunching, it turns out to be about 418 kilojoules. And the next step then, once we have the liquid water at the boiling point temperature, we need to turn that to gaseous water at the boiling point temperature. So this is where we have to incorporate the latent heat of vaporization. So the heat added Q is equal to the mass of our substance times the latent heat of vaporization, which you once again look up in a table. Okay, that latent heat of vaporization has a value of about 2.26 times 10 to the 6 joules per kilogram. Notice that the latent heat of vaporization is much, much bigger than the latent heat of fusion. It takes a lot more energy, okay, to move those liquid particles from a liquid state to a gaseous state. You've got to move them very far apart. A lot more energy required to do that than to move solid particles a little bit further apart for them to enter the liquid state. So here we will finish this problem on the next slide. So continuing where we left off, okay, the last step in the process is now to take that 1 kilogram of steam at 100 degrees Celsius and convert it to steam at 120 degrees Celsius. So once again, for this process, there is no change of phase required, right? We're starting with steam, we're ending at steam. All we're doing is bringing about a temperature change. So we're justified in using Q equals mc delta T, okay, for the calorimetry of the problem. We plug in our numbers here, once again looking up the specific heat capacity for gaseous water, for steam, okay, which has a value of about 2.01 times 10 to the 3rd joules per kilogram degree Celsius. We do the number crunch and we end up with 40.2 kilojoules. Now remember, the problem asks us to find the total amount of energy, okay, required to bring 1 kilogram of ice at negative 20 degrees Celsius up to steam at 120 degrees Celsius. So this requires us to add the total amount of heat we figured out in each step, okay, to get the total amount of heat for the entire change we're talking about here. So when we add up all of the heats from each of the steps, we end up with a total amount of heat added of about 3,093 kilojoules. If we were to construct a heating curve for this, and I have done this here in graphical analysis, this is what it looks like. First of all, notice that it takes the same characteristic shape that we talked about qualitatively on a previous slide. You will notice that we have the three sloped portions of the graph, which correspond to a temperature change, or microscopically speaking, we're adding heat to increase the kinetic energy of the particles in our substance. And then we have these two characteristic flat portions of the graph corresponding to the phase changes, where the heat added doesn't go into increasing the kinetic energy of the particles, but rather goes into increasing the potential energy of the particles, okay, in this case to move them further apart, okay, to bring about the phase change. So we're asked a question here, why are the latent heats of vaporization greater than latent heats of fusion? You'll notice here, the latent heat of fusion here, okay, has a certain amount of heat that's added, okay, which is much less than the second flat portion here, okay, which is a much greater amount of heat corresponding to the latent heat of vaporization. Why is this? Well, I briefly alluded to this in the previous slide, that what is happening? Well, remember, what is the difference between a solid and a liquid and a gas? To take solid particles and turn them into the liquid state, okay, we have to move them a little bit further apart so they now have some rotational freedom to move around each other. That takes a certain amount of energy to do that. But to take those liquid molecules and turn them into gaseous molecules, okay, we are greatly increasing the separation distance between those particles. Okay, we're actually moving them so far apart they can entirely escape the forces of attraction towards each other. This requires a whole lot more energy, okay, to do that. So in general, you will find that for any substance, okay, the latent heat of vaporization is much greater than the latent heat of fusion, meaning that a whole lot more energy is required to, in the form of potential energy, to move those particles further apart to go from the liquid to a gas than is required to go from a solid to a liquid.